5 points. Oh, 24. What did 24 say?
Wait, why is the camera blurry?
Huh?
Wait, I think there's...
What the heck? Oh, there we go. We got it back. We got it back. There we go.
What's the thingy?
Okay, how do we do this one?
You just put it on the formula. F prime of C equals F of B minus F of B.
Right, so the derivative is defined everywhere. I guess we are supposed to also assume it's continuous. This way we can apply the mean value theorem. We know that F prime of C at some point for some C in the interval 2, 8, F prime of C should be equal to F of 8 minus F of 2 over 8 minus 2. So we know that here 6 F prime of C is equal to F of 8 minus F of 2. And how do we go from that to what we want?
You multiply F of, you just multiply that, right?
Use either 3 or 5.
Well, see, F prime of X is also equal to F prime of C.
So this is F prime of X, which is this.
Yeah.
Now we are told here that it's bounded by 5 and 3. So this means 6F prime of C is between 5 and 3 times 6 times 6. Right? By that rule. And so 18 less than 6 F prime of C less than 30. But this guy we know is that guy. Just multiply this inequality by 6 everywhere, and I get this one. And then I know that I can replace with this by the mean value theorem, and so we get that. Other questions? 25. What does 25 say?
I guess that Q is in it over.
Is there such an F where F of 0 equals minus 1, F of 2 equals 4, and the derivative is less than 2 for all x?
What's that QED?
It just means the end of a proof. It's the math. Don't worry about it. Who knows what that stands for?
Belongs to the principle.
Question.
Question ended.
Never mind.
Question ended.
It's not in English. Never mind. Okay, let's go.
He said it's not
Wait, no. No.
It's Latin. It's not important.
Where?
Just tell us.
I How do you go?
Now we're gonna think about it for the rest of the
Let's just Google when we get home.
Ideas for how to do this.
This one, we'll just try.
How have you applied the mean value theorem?
Professor, I did this like the other way, like without using that, like mean value theorem. Because you know 0 is x, f of 0 is x, right? And f of 2 is x1. And negative 1 is y1 and 4 is y2. And I just found the slope and compared that with the.
Okay, so we know that when x is 0, one of the y values is -1. And we also know that when x is 2, the y value is 4. So this here is the secant line. Its slope is the average rate of change.
Code error demonstrator.
You looked it up, that's cheating. No points for you. Okay. So what is the slope here?
The slope is just y2 minus y1. That's y2 is
So the rise is 5,
yeah 5
and the run was 2,
yeah,
which
so
is,
2.5
it's bigger than 2 in particular.
yeah.
Right? So would you be able to find such a function?
no.
Such a function
There's not
cannot exist. It would violate the mean value theorem. Here's a question. What if the function wasn't continuous or wasn't differentiable? What if I had jagged edges, or I could do an asymptote or something and try to make it hit these points and keep the slope below 2? Would that be possible?
no. No.
Because remember, to violate the mean value theorem, it means I'm assuming the function is continuous and differentiable everywhere. We know it's differentiable, but maybe I could mess with continuity and get a function that does this. How would I be able to do that?
Without by messing up continuity.
Yeah.
Maybe you can do it by, you know, what do you call that? You know when you separate and you have those
Point?
dots? I don't know what you call that.
So you're thinking, okay, so let's try to create a function that actually does this and see if it can work. But let's not be continuous, right? Let's say, what if I made the slope 0 until I get here, I just jump here.
Yeah, that's what I'm saying. Like,
The slope of the function is less than 2.
yeah.
Does this work? Are we wrong here?
Yeah.
What's wrong here? What would be wrong with this example?
It does not have the slope. Right? No, slope is not there. No, it's not differentiable. No, it's not differentiable. No, slope is
The derivative wouldn't exist
yeah.
here. It wouldn't exist at 2 because there's a jump. Right? So then this would be irrelevant. So even if you try to come up with a weird example, you're going to break something somewhere. Right? To make everything nice, it just wouldn't work because it would contradict the mean value. So don't think you can get away by making gaps or holes and trying to jump somewhere. Because once you do something like that, your slope here is 0, your slope here is nothing. You can't even take a limit here. Right? So it would contradict the derivative existing. So there really is no way to make a function that does this. Doing like 3/5 of the homework now.
You're going backwards.
How small can F4 possibly be? Again, here I use value theorem. I know that f prime of c is equal to, I can use f of 4 minus f of 1 over 4 minus 1. This means that 3f prime of c is equal to f of 4. F of 1 was 10. So this means that f of 4 I'd be able to write as 3 times f prime of c plus 10. And now what do I know about f prime of c?
F prime of c has to be greater than or equal to
It has to be bigger than or equal to 2. This means f prime of 4
is equal to
should be bigger than or equal to 3 times 2 plus 10. Okay, let's talk about derivatives and the shapes of graphs. Which is going to give us a nice segue into curve sketching, which is a big topic. Okay, so just some context here. Remember we are alright, quiet down, we're about to start. So remember we've been dealing with functions a lot in this class pretty much the whole time. And the whole point of functions is to, model real world situations, dependency relationships, right? So of course there are several behaviors we want to be able to keep track of, right, when we're modeling things. So for example, let's say, I have my own company or something, and I have my analysts trying to figure out, how my profits are behaving, right? So they create this function that's supposed to describe my profits, right? What are some of the things I want to know? When are profits going up? When are they going down? Are my profits increasing? Are they decreasing, right? This helps me make business decisions, right? By knowing how this profit function behaves, right? I'd want to know, when is it going up? When is it going down? And if I know it's going up, I'd also like to know how it's going up, right? So if I know my profits are increasing by $10 a week, right? Every week I make $10 more than I made the previous week. It's a very different thing than if my profits increase $10 this week, then $100 the next week, then $1,000 the next week, right? It's a completely different scenario, right? Now as a businessman, if I'm increasing by $10 every week, okay, I'm making money, but how do I make that better, right? So there's a certain sort of behavior. It's not just about increasing. It's about how we're increasing, right? So all of these, and of course there are maximums and minimums. Do I have a maximum profit that I can make? Is there a minimum profit that I can make that I have to get better at, right? So there are all these things that I want to be able to tell about my functions. Where is its maximums? Where are its minimums? Where is it increasing? Where is it decreasing? How fast is it increasing? How fast is it decreasing? Things like that. And it turns out that derivatives can help us describe these behaviors in a very nice way. So let's jump into that. So there are so some of the first ones were absolute, and relative. Alright, so mins, we already dealt with this, so I'm not going to say more on that for the moment. Another thing is going to be behaviors like increasing and decreasing. And what do I mean by increasing and decreasing? F of x is increasing on an interval I. If, how do I know a function is increasing? Well, that's how we can tell. I'm really asking for a definition. Basically, this means if x2 is bigger than x1, then f of x2 will be bigger than f of x1. Right? This basically says, i.e., as x values increase, the y values will increase. I.e., the graph goes up as we move from left to right. The graph of f goes up, moving from left to right. So in other words, your function will have to behave something like this, right? Here's an x1, here's an x2. The y value for the last one will always be bigger than the y value for the first one. So your function is doing that sort of behavior. And it turns out, of course, if we measure this by a tangent line, try to approximate at any point, the slope will be positive. And this is how we can tell that something is increasing by looking at the first derivative. Because the graph is moving up as you go from left to right. Right? That gives you a positive slope. Similarly, right? So this means your y value gets smaller as you go from left to right. And if you sort of draw a picture of what this means if x1 and x2, your y value in the last point is lower than the y value in the first point, your function will have to behave this way, and in this case your slope looks negative. And this leads us to that theorem that everyone shouted out the first time. Proves that it is differentiable on I. 1. F is increasing. I is just an interval. On I if f prime is positive. So this is how we can tell about increasing and decreasing. We sort of just look at our function, how it behaves, and then we can see that, oh, the slope would have to be negative to achieve this behavior, or the slope will have to be positive to achieve the increasing behavior. And so that's how we can tell about increasing and decreasing. We can actually use the first derivative. That's going to be a very important concept. Okay, so what about the other behavior I mentioned in my example, right? So let's say my profits are increasing by $10 every week, as opposed to increase by 10, then by 100, then by 1,000. That sort of behavior in math is described as concavity. So when we're talking about how something is increasing or decreasing, that's talking about concavity. And this brings with it its own shape on the graph. So you can sort of intuitively see what increasing and decreasing is on a graph, but what does it mean to have a certain concavity? We're going to make that precise now. F is concave up. That's what it's called. If F lies concave up on the interval. If F lies above its tangent lines. On the interval. So, illustration of that would mean the following. So here's a function, right? I'm on some interval I. Notice here at any point, if I draw a tangent line to here, or to here, or to here, notice that the function is always seen to be like standing on top of its tangent line. The tangent line is always under the function, right? This behavior is called concave up, right? It doesn't have to be increasing to achieve this behavior, by the way. You could be concave up while decreasing. Your function could look like that, right? Notice that every time I draw a tangent line to this curve, the tangent line ends up below the function, right? Whenever a function has that shape, we call it concave up, right?
Professor,
Yes?
the x-axis, are we calling it I?
I'm just saying the interval where I'm observing this behavior. It's just an interval on the x-axis, right? The function could switch behavior somewhere else. But I'm just saying, I'm looking on some interval of the function. If I observe this behavior, it's called concave up. This is called concave up. And a lot of times remember up like a cup. Right? That's how you remember that shape. Up like a cup. That's concave up.
Smiley face.
Smiley face, right? And that's going to have more meaning later on. You know, when you're feeling up, you're happy, you're positive, there's going to be some connection to being positive. And what's going to be the connection? What's happening to my slope here? My slope is increasing, right? So if I think of my slope as a function, how can I tell if that function is increasing? Find its derivative and check if it's positive, right? This happens if f prime increases on I, right? Here, my slope was like 0, now it's positive. Now it's more positive. Now it's more positive. The slope is actually increasing to achieve this behavior, right? So what does that mean? This means if I take the derivative of this guy, it should be positive. That just means the second derivative is positive, right?
Wait, I don't get that part. If you take the second derivative, it's positive.
Yes. My slope is increasing. How do I know when something is increasing? The derivative is positive, right? That's what I just said here. If a function is increasing, the derivative is positive. I know f prime is increasing, so its derivative should be positive. But the derivative of f prime is just f double prime, right? Yes?
That one right there, is that also positive slope? The second graph.
It's not positive slope. That's not what's important. The slope is increasing. Here it was negative, and now it's turning positive, right? So the value of the slope itself doesn't matter. The fact that the slope is increasing is what matters, right? Yes?
So the f of double prime, if it's positive, is concavity up.
Yes. So I'm going to put this on the theorem. Concave down is another thing. And by the way, this is what I meant about positive, right? Up like a cup, you're up, you're smiling face, you feel happy, positive. We're all feeling positive, okay? All right, concavity, concave up, second derivative positive. Okay.
So,
Trust me, it's gonna be important.
so what are the lines?
Huh?
Are the lines F?
These lines, the straight lines, these are the tangent lines.
So these are F prime.
So the slope of the lines is F prime.
And what's F double prime?
F prime is the slope of the derivative. It just means the second derivative. You take the derivative and you take it
But
in.
where's the second derivative of the graph?
You can't really see it.
No.
It's like if you were to map these slopes as a function, like you plot the points for the slope, draw that graph. We'll have an exercise like that. You'll see it. Alright, why? So now F is concave down if it lies below. So you have an example like here. That function is concave down on this interval. Why? Because every time I draw a tangent line, the tangent lines will be on top. Right? By the way, the function doesn't have to be going down to be concave down. I could be going up and be concave down as well. This is also a function where the tangent lines are all on top, not on the bottom. But what do you notice about the slope of the tangent lines?
It's getting more, it's getting negative.
It's decreasing, right?
It's decreasing.
Here it was even positive. Now it starts getting smaller. It starts to get negative, right? Here you see F prime is decreasing in all these cases. Which means F prime, its derivative has to be negative. That is, the second derivative is negative. And that gives us the next theorem. If F is concave up on I, if F double prime is positive, right? And concave down, down like a frown, right? That's how you remember. Concave down, down like a frown, right? So it means you're sort of like a frowny face, right? Concave up like a cup, you're like a smiley face, right? So concavity is talking about the shape of the graph. And it's very important that you note it's not talking about increasing and decreasing. It's something completely different. You can be concave up and increasing. You can also be concave up and decreasing. You can be concave down and decreasing. You can also be concave down and increasing. It's not talking about increasing, decreasing. It's talking about the shape. That's why I give you this mnemonic for you to remember. Concave down like a frown. It's just talking about the shape, right? Up like a cup. It's talking about the shape of the graph.
Professor,
Yes.
is there any meaning behind not touching the x-axis?
No, there's no movement.
Because I know in your graph you haven't touched the x-axis.
Okay. So that's increasing, decreasing, and concave up and down, right? So, and it's going to be very important for us to figure out when our function exhibits these behaviors. So that's what we're going to try to figure out. How do I know it's going to be concave up or concave down? Or how do I know it's going to be increasing or decreasing? Well, the derivatives tell us. So let's see how we figure them out. So before this. So now we know increasing means you're going up as you move from left to right. Decreasing means you're going down as you move from left to right. Concave up means you shape like a cup. Concave down means you shape like a frown. Okay. There are things called inflection points. This is an inflection point is a point where you actually switch concavity. So if you have a point on your graph where you switch from concave up to concave down, or you switch from concave down to concave up, we call that point an inflection point. So what would that look like? Here's a graph. What is that behavior? Concave down, shapes like a frown, right? Now let's suppose I pass some point, and from that point on, I go like that. Now I'm concave up. Frown, here I'm like a smiley face. This point here is called an inflection point. Right? And there's nothing special about going from concave down to concave up. I could go the other way. I could be like this, and then I switch to that. This point is an inflection point. Right? So notice here on this from here onwards, I was concave down. I passed this point, and then suddenly I switch to concave up, right? Whenever I make that switch of concavity, I call that an inflection point. Here, I was concave up. I passed this point, and then suddenly I'm concave down. I call that point an inflection point, right?
What if there's like a line that is just like a straight line before it changes?
What do you mean?
Inflection would be in the middle of the line.
It was a straight line and then what?
Like start doing in front of making it positive knockdown. Like draw a positive like
You mean concave up?
Yeah, concave up.
Like this?
Say go straight. Yeah.
Then straight?
Yeah. Nah, like a straight line.
Diagonal.
Okay, like that.
And then go to concave down.
And then go to concave down?
Yeah,
like that?
where would the point?
Middle.
In the middle.
No, in the middle. In the middle.
Oh, right, yeah. The line is still.
It would, technically it would be in the middle if you compute it, yes.
Okay, that's all.
Right. I'm going to tell you how to specifically find these points, so you'll see how to compute it. Yes, in that case you take it to be in sort of the middle. Okay, so now let's pay attention to this. Okay, so let's go through this. I'm talking about a function f. We're going to assume it's differential and continuous for the moment. Let's say we're just dealing with nice functions here. Okay, what does the original function tell you? What does f tell you? Y values, right? What it can tell us? Y values. Or points on the curve itself.
original graph.
Right, the original graph. What are the points on the graph itself, right? So you know, at any time, if you're looking for the points on the graph, who do you look at? F, right? If someone asks you points on the graph, do not look for the derivative. Do not look for the second derivative. You look at F, right? There are going to be problems where we have to be looking for a lot of things at the same time. I need you to understand where you should be looking. If you're looking for a point on the graph, look at F. Do not look at F prime. Do not look at F double prime. If you're looking for a y value of something, look at F. If you want to find a y value, what do you look at?
F prime.
Okay. There's no real condition. I mean, you find by coming into the graph. We know how to deal with that. Okay, what does F prime tell us? What are the things that F prime can tell
Slow,
us?
positive, negative.
In terms of behavior of the function of the graph,
Positive, negative.
it can tell you. It can actually tell you where maxes and mins occur. It can tell you about increasing or decreasing. Right? That's what, as far as the shape of the graphs are concerned, that's where the derivative helps us. If I want to figure out where are the maximums, where are the minimums, where is it increasing, where is it decreasing, the first derivative is where I'm going to look. Right? What are the conditions under which it tells me these things? Well, increasing, we know that that's easier, right? Increasing just means wherever the derivative is positive. If I want to find where it's increasing, I'm just going to find the derivative, figure out where it's positive, right? If I want to figure out where it's decreasing, I'm going to find the derivative and figure out where it's negative, right? So for increasing and decreasing, those are the conditions. How about a max? How do I know when something is a maximum? Yeah.
If something is increasing first, then decreasing, that's max, and vice versa, that's it.
Right, so we know that this point here is a maximum if you're increasing on the left and you're decreasing on the right, right?
It's just for relative, right?
For relative, yes. These are relative, yes. Relative, right? So it means, how do you know something is a maximum? Well, the first derivative is positive on the left side of it, but it's negative on the right side of it. In that case, you end up with a maximum, right? Of course, the opposite would be a minimum. And of course, I'm assuming that the function is actually defined at this point, right? If there's an asymptote or something, of course, all bets are off, right? But assuming the point is defined, I know it's a maximum if the derivative changes sign from positive to negative. That means actually went like that, right? That will actually tell me max or min. I'm sort of running out. Well, min, of course, is similar, right? Running out of space. You know you hit a minimum if you were decreasing first, which means your derivative was negative, then you started increasing. Right? That means you will hit a minimum, a relative minimum.
Would that be concavity? Would that be?
It has nothing to do with concavity. First derivative, max, min, increasing, decreasing. Concavity is a whole
No,
different story.
Second derivative.
So how we can find it? Well, there's something called the first derivative test. Here's the test. Find all critical points. That's step one. 2. Put these on number line. 3. Test the intervals. 4. Conclude based on the sign of a prime. We're going to run out of time before doing an example, but we'll pick up with examples next class, I guess. I'll just write down one for the second derivative. We're actually going to do the second derivative test. The first derivative test and the second derivative test. Function. F double prime. What it can tell us. I know how we find it. By the way, what I'm trying to help you with here is algorithm recognition, in case you didn't recognize it. Right? It's just something that's supposed to trigger a sequence of steps in your head. If someone says increasing, boom, in your head, this is what you see. You don't get confused, oh, this function looks ugly, there's a pi. No, that's not what you think about. You think about this, and it keeps you focused. You know what you have to do. I'm just going to find the derivative, set it equals 0, find where it's undefined, test the intervals, right? You just go into this mode, right? You're like, you're a machine, you just kill it. You don't care what it looks like, you just kill it, right? Algorithm recognition. Okay, F double prime, what can it tell us? It can tell us about concavity, right? This means concave up or concave down. It can also tell us about inflections. That's what the second derivative can tell us about as far as the shape of a graph is concerned. How do we know? Well, concave up means the second derivative is positive, right? Concave up, positive, feeling happy, up like a cup, smiley face, right? All these things go together. Concave down, second derivative is negative, feeling down, not happy, frown, down like a frown, right? And what you have to remember is that this goes with a shape, right? It goes with a certain shape. Concave up just means you shape like a cup. Concave down means you shape like a frown. And you can be increasing or decreasing while you're doing this, it doesn't matter. It's talking about the shape. Right? How do we know it's an inflection point? Well, it means you have to switch from concave up to concave down, right? So an inflection is something like this, where here the second derivative is positive, and then it switches to negative, right? And I forgot to mention, like at this point here, it would be 0. But I'll mention that later on. Same thing for max and min, right? We actually showed that before, I believe. The derivative would be 0 at a max or min, but it would change sign on either side. Inflection is the same way. The second derivative has to be 0 there, and they change sign. So this would say, on this side, I'm concave up like a cup. On this side, I'm concave down like a frown, which means this point would be an inflection. And of course, vice versa, the same thing holds true. And here, we can do the test. It's not called the second derivative test. The second derivative test is for a special thing. We'll go over that next time. But again, one, find the second derivative. 2, find its critical points. 3, put these on the number line.
'Professor,
Yes.
for the second derivative, the original function, which one would you use as the original function? The original function itself?
It'll be given to you, right? So I'll say, here's a function, and I'm going to ask you to do something with it, and based on what I ask you, you're going to know I need the derivative or the second.
Yeah, because what I was thinking was, for first derivative, right? The original function would be the original function. And
Yes.
what I thought in my mind was, for the second derivative, the original function would be the derivative.
First derivative, yes. Second derivative just means the derivative of the derivative. So you don't look to the original function, you look to what you
But in the
differentiate.
critical points, you have to put the points that you get, right?
The critical points of the second derivative, which means they're going to set the second derivative equal to 0 and undefined, and put those
What is that
on.
going to be the inflection point?
It's only an inflection if this happens.
Oh, yeah,
If it's
yeah.
0 somewhere and it switches
Yeah.
signs,
Oh, yeah.
then that gives you an inflection. Okay, so the moral of the story is you need to know if I ask you for something, where you get it. If I ask you for, what is the y value at this point? You know you have to look at f. If I ask you, where is the function increasing? You look at the derivative. What is the concavity? Where is the concave up? You have to look at the second derivative, right? Based on what you want to find, you have to look at a different function. And we're going to do examples of all these, and we'll talk about second derivative tests next time. But we'll end there, just so you have an idea of where we're going.
What is it?
Yes.
What would it be the inflection point? Inflection point. What would the inflection point be in a circle?